I think all right. Huh? It doesn't make any sense. There we go. Let me do that. All right, good morning, everyone. We're ready to get started with the Measurement Analysis for Protocols Research Group meeting here in Chicago. I'm Dave Plonka. I'm with Akamai. This is Mirya Kulavin, who's with ETH Zurich. This is an IRTF research group meeting. We use the same intellectual property rights as the IETF. This is the stuff that you clicked through when you signed up to come to the IETF meetings, but it's again here for your perusal. What we're going to do today is start off with an introduction to the group for those of you who haven't been here before, and go through the agenda. And we'll have a couple short advertisements for a couple projects that that are just one slide, and then we'll move on to 9 presentations that we have for today. Administrivia, here's where our charter is. We won't go through the details of it, but the gist of it is that Measurement Analysis for Protocols Research Group is meant to bring nascent measurements and measurement techniques to the IETF that are about work that's going on in the IETF. So have a measurement basis for to support some of the engineering decisions that are made, and also to track operationally what's going on. So to support both the engineering of protocols and the operation. There's a mailing list that we post the call for contributions, for instance, to the group. So sign up there if you want to participate in the group in the future. We also post the recordings and the links to those there. Today's slides link is right there, and remote participation is available by audio stream, Meet-Echo, and Jabber by those URLs.
And thanks a lot to Wes for taking this.
So in our preparation for this meeting, Mirya and I did the same thing we did last time, which is, I guess, unusual for IETF meetings. We did a call for contributions, sort of like you would do for an academic conference, and ran it through the mailing list, requesting an abstract weeks in advance so that we could match up the work to other groups, other efforts in the IETF. We received 14 proposed contributions in addition to the one from Mirya and myself. So of 16, we chose 9 to be presented in full today, neither of which are ours. And so thanks so much for the proposals. It's an embarrassment of riches to be able to choose from so many things. It's regrettable, though, that even in 2.5 hours time, we don't have time to show all the contributions. And so we either suggest that they develop the work a little more and come at the next meeting, or we turn them into advertisements for the project here, giving them the 3 formats that we're using. You can have like a 1-slide advertisement for your project so you can network with people through it, or you can have a short presentation if it's a project that doesn't have many results yet, or a long presentation. In this case, they'll be 10, 15, and 20 minutes if they're delivering measurement results. So if you have different ideas about how you'd like it to be run, feel free to share that with us on the mailing list. Charter notes, this is exactly what I said before about the things we focus on here. So the agenda for today is, following this introduction, will be Matt Mathis will be presenting about refreshing of MLab, and I still can't spell refreshing, it's spelled it twice. Corey Fairhurst will talk to us about low effort code point, the DSCP code point, and preliminary results that they've been finding. Padma Bhuma is going to come and talk to us about TCP ECN, I guess, experiences with Apple implementations about enabling ECN. And then Tommy Pauly is here, also from Apple, to talk about measurement trends in V6 support, and I think what's going on with happy eyeballs there. Tobias Biebig is going to talk to us about global scanning of the IPv6 internet using the IP6.ARPA space. And I guess I would say a couple of these are talks that are really nascent. They're about to be published. So for instance, Tobias' work is one I think that's going to be in PAM later this week. So we're bringing some things to you where you're getting an early view of those. Similarly, Giovanni's work here about no domain left behind, measuring Let's Encrypt, that's something that is in the process of being reviewed for publication. So you're seeing an early version of that. Great opportunities to give them feedback to improve their frameworks. Rolf Winter then next will talk about how broadcast data reveals your identity in social graph. And then Marcella Hastings about weak keys and widespread in network devices. And this is one that Miri and I solicited for, specifically because we're after things that are IoT-like measurements. And in Maprg, some things were both in IoT and V6 where measurements were quite low. Those were things we tried to pull out. So we always solicited Tommy's and Marcella's in that respect. And then lastly, we'll finish up with Will Scott's presentation about open measurement of internet censorship, and I think that's tied to the Tor project. So our 2 slides that are advertisements, I wanted to give you a little glimpse of what we're seeing with V6 lately at Akamai. The graph on the left is the count on the blue line is a count of addresses per week that we see hit the Akamai platform. So up to 4.39 billion V6 addresses per week. You can see the slope of that growth over the last 3 years is quite significant. On the right, I'm showing you the decline in tunneling technologies like 6to4, where it's cut in a third over the last few years. So good news. And then another link there at the bottom, the 6XS project is decided to shut down. So they're sunsetting, and that was a tunneling-based V6 project that tunneled over GRE and gave you native V6. So a lot of real native traffic and a couple of the tunneling efforts are certainly on the decline. So that's the V6 update. And then we have a one more advertisement for this project from Zhihong Deng. And so she's here if you want to talk about this one. I don't know much of the context other than what the slides here, so check it out there. And again, a project advertisement that she may be doing measurements that could come to a future research group meeting. So we got the blue sheets going around. Is that true? They're going to be going around, so please sign up. This has always been a well-attended research group, and it looks like it is again today. Please sign up so that we can see the level of interest. So first up will be Matt.
Good morning. I'm here to actually plug some stuff that we're doing at MLab, and it was kind of refreshing to see an MLab reference on the previous advertisement. How many people here are familiar with Measurement Lab? with MLab, vaguely. How many people are not familiar with it? I'm going to ask it that way. Okay, Measurement Lab is a global collaboration to measure the internet. It's almost entirely focused on user access. And what we have is a radically open platform. It's open data, it is open source. There are a few pieces of it that are not completely open, of course, things like credentials and stuff, but and a part of the data processing is not currently open. We're migrating to completely open systems everywhere. And it's a global platform. And I'm sorry, I have to stand really awkwardly to look at the slides. It's been around for a while. I actually started collaborating with Measurement Lab as an external independent researcher. Earlier on, it used to say our independent researchers as part of the collaborators before I started at Google. And I actually came to Google by way of getting involved in Measurement Lab and then work here. That's not an advertisement for that route, by the way. So we have a fairly large footprint, 100 servers globally. All of them have 1 gigabit connectivity, even in places where 1 gigabit is the entire ISP. There are a few of those. We get roughly 300,000 tests per day. These are at some level user-initiated tests. In a few cases, there are users who deliberately launched scripts to do repeated tests. But most of the tests are actually people clicking on something to get a test. We have a huge archive of data. I believe it's 5 petabytes now. It's steadily growing. And a lot of stuff in BigQuery where you can do an SQL-like accesses to data, tabular data of various forms. And there's a whole bunch of visualization stuff. Almost all of the code to do this is open source and readily available. You can see what we're doing to understand our methodology and all that kind of stuff. We are planning, I should say it's built on Planet Lab technology, which is kind of custom and kind of out of date. We are building a new infrastructure, fleet-wide upgrade of essentially everything, all of the hardware, all of the switches, all of the operating systems. We're going to newer operating systems, including operating systems that will have available in them BBR, although we don't have a plan for how we're going to use that. Modern virtualization, containerization infrastructure, which means that you can do prototyping in a regular academic lab, for instance, will make things much easier. And in some places, we're going to 10 gigabits and a bunch of other things like that. And we're also building out our footprint in Europe. Part of this is going to involve restarting the experiment, rebooting the experiment approval process and the experiment release process. And that's really why I'm here, is we're going to be sometime this summer looking for additional collaborators to run additional experiments on the platform. And that's really the message that I wanted to communicate. We're always looking for people who are interested in doing data science on our archive. We have a lot of data and a lot of interesting things in it. And for instance, the talk that was just mentioned is a data science study. Lots of good things going on. Any questions? Going once?
I guess I have one, Matt. The new deployment, can you give us an idea of the scope of it? Locations, machines, networks you think will be in?
So we're currently, the platform refresh is going to upgrade essentially all of the existing hardware, or the vast majority of existing hardware. And I don't actually know the count, but we're building the European footprint to look more like the US footprint. And in the US, we have multiple servers on different ISPs in about half a dozen cities, half a dozen metros. So you can do differential measurement between access ISPs and transit ISPs in the same metro. In fact, that happens by default.
Okay, thanks.
These kinds of things are very useful for discovering odd differences in performance.
Wes Hardiker, USC. Looks good. I look forward to seeing what I could do with it sometime this summer. But could you give us some examples of research that has been done on it and sort of interesting findings?
So there are a couple of things. There are a lot of people who try to mine understanding of, well, the measurement is focused on access. We don't permit on a standard basis automated tests node to node, because we know those paths are pretty well engineered and we know what they are, and you can't measure them without actually being disruptive. So it's all access measurement, and we're trying to infer things about what kinds of equipment people are using, what kinds of connectivity people have, what kinds of end equipment people have. There's a lot of things you can actually infer from the data. So
let's go to Robert.
Robert Kushtekir, IPCC. Thank you very much for your work. It's really appreciated. We are already using this data in RIPEStat to show per country bandwidth measurements changes over time. So if you're interested, you can just go there and basically we channel the data that MLab already has. That's already really good. And there is some collaboration work in the making about storing RIPE Atlas data as a second site or something like that, streaming to users. Because we also have a lot of data, and we are, it's useful to have second sites as well. So thank you again.
Yeah.
Thanks, Matt. All right, next up we have Gori Fairhurst talking about the low effort code point.
So let's see how I can manage to see behind me as well. I'm Gori Fairhurst. I'm going to present 3 different tools that we've been using to look at traversability of diff-served code points and try and show 4 results all within 6 minutes. So we'll see if that works. The basic challenge is to see whether we can build a scavenger class diff-served code point, which is working TSVWG, and therefore whether the code point that we might select would actually work. So the first tool is PathSpider. You may have heard of PathSpider. It's being used for testing ECN and other things. In this particular use, we're going to use PathSpider to check whether the diff-served code point 0, the default one, traversed between vantage points provided by DigitalOcean to the top 1 million web servers from the Alexa Web Million. We did tests that tested diff-served code point 0 and the new proposed code point 2, and we discovered 99.998% of paths could perform a 3-way TCP handshake using both code points. Hence, we conclude that setting a DSCP did not black hole packets within the server to data center path, which is good news. So the first piece of good news. Next question is, what code point was actually used to reach these servers? It's all right to say you set a code point at the sender in the packet. It traversed a series of routers along the path. Did the code point actually get changed on the path to the servers? Well, to do this, we did a expanding ring search using TTL. So we set the TTL to 1, sent the packet, and looked to see what the ICMP message contained, had the diff-served code point changed. And then we repeated it with 2, 3, 4, etc. We used 300 targets and looked to see what happened. And the results show, well, all of them got through, which is good because that's the same piece of information I already have. 81% of paths were unchanged, 90% of paths remarked to be E, so they bleached the code point at some point in a router on the way. In fact, this is good news as well, because for the diff-served code point used for scavenger class, this simply upgrades it to best effort, which is kind of okay. It's not really a bad thing. So, good. Another bit of good news, TCP and UDP results were absolutely identical, which is what we hoped for, because so nobody should be looking at that. So that's good. Next question. What happens to other diff-served code points? And this is the not so good news. What happens when you set a diff-served code point that isn't 0 or 2? What's the chance of actually receiving a diff-served code point 2 along the path by one of the routers remarking? And the answer is it's quite high. about, I'll go for the next slide. About 17% of routers along the paths we tested, these are routers that saw more than 30 different diff-serve call points and reported them, actually bleached the upper 3 bits of the diff-serve field. They set those to 0. This is almost certainly because they're using some TOS semantic, which has been around for a long time, and it should have been obsoleted. People shouldn't be using it anymore, but people evidently are widely using this bleaching method, which means that diff-serve call points in the AF group, AF anything 1, AF11, 21, 31, 41, have a high probability of being remarked to diff-serve call point 2. This is where measurements are actually useful, because that means if you try and set the diff-serve call point to a higher value to get a better forwarding treatment, you might end up actually being reassigned to scavenger class if we implemented diff-serve call point to a scavenger. So at this point, you begin to wonder, is this good or is this bad? I mean, it's better than for CS1. It's maybe not that good because it's a real priority inversion. Solution number 1, we go and fix all these routers. Unfortunately, these are routers that are using configurations which are more than 10 years old, so that might be a bit tricky. We could just wait for them to fail, or we need to look at other options. So the final tool I'm going to just mention is a tool called Edge Trace. This is a tool that does the measurement again, but this time from your own computer. What we're trying to do is gather some data from people's access networks from the edge, because all the previous measurements were taken from data centers rather than from edge computers. Edge computers probably do other things because they go via access providers, many of whom will have policies. We know results for many cases, but we don't have good results for a wide range of diff-serve call points. So we wrote a tool in Go, and it simply sends a web request, retrieves a token, and then sends 270 UDP packets at 5 packets per second, exploring all the different code points in a set, and it plots the answers out at the end. I'll show you the URL to play with that. We'd love people to play with that tool and help us gather good data. So please, please, please look at the tool. Please, please download it. You can fork it on GitHub, look at how it works, change it, whatever you like, but please use it. But please don't use it in the IETF meeting room, or else we'll have 1,000 samples of what the IETF network does, and we already know this. So this is one to take home. Okay, takeaway messages. DSCP2 had good survivability. Rumors that diff-serve call points cause your packets to get dropped in the core seem to be not true, so that's good. You can use any diff-serve call point, more or less. It's not affected by the TOS semantics, but there are side effects because other traffic is affected by TOS semantics. So we have to be careful, and I guess we have to go back to TSVWG and rethink. One other thing we discovered, OpenSSH uses code point 2. If you look at the compiled code, it's used this for a long time, probably dating back to the old TOS semantics. And nobody changed it, uses 2 and 4. So there is a bug report for that. There's something in my extra slides that talks about this, so go look at that if you like. If you're able to influence that, do. However, it probably influences firewall configurations, so it's probably hard to change. Finally, questions and answers, and the URL for the trace tool. And if you go to the URL, you can download the tool by just clicking, but also you can see the data we collected. Okay, very lightning tour, but hopefully interesting because it's influencing real work here. Any questions?
Thanks, Corey. It looks like next.
So I've had a conversation with some home router vendors who point out that one of the queuing disciplines implemented in the Linux kernel, which is often used for home router box, although it doesn't bleach the bits, it actually inverts the semantics of that bit, which is a different class of problems.
This is a bit like the 802.11 mapping problems. This is mapping to the correct PHP.
Yeah, that's probably where it happened. I don't know the details of it, but it's an aspect that you can't measure with this technique. And
yeah. This technique is purely trying to say, can we actually use these code points? Behind that, you have to have useful PHPs, but if you can't use them, then you can't do the PHP thing at all, except locally.
So one of the things that's an important effect here is since none of this has ever really been deployed, there's no interest in getting it right. And so people, you know, they're setting up the router, they come to the section that says setting up your classifier, they skip it. And if anything became deployed, I bet a lot of these problems would become fixed fairly quickly. Some of them, of course, have this infinite tail. But that's another story.
Yep, I agree, Matt.
You said something about code point 5 yesterday?
Yeah, well, I was going to go back and suggest code point 5 as being a possibility because it doesn't bleach in the same way, and therefore we could deploy it. Maybe we should be scared about a scavenger class because it's supposed to soak up all the remaining traffic and be lower in quality in terms of getting forwarding access. And we don't want that one to be inverted. Maybe other things can take other code points, but this one we should be cautious with. And it looked to me like 5 might be a good number.
So did you have any cases where 2 got inverted into something that looked like it was higher priority?
2 becomes 0, which is default.
Oh, well, okay.
That's okay.
That one you expect.
Yeah, higher priority stuff can get remapped to 2, so we make 2 lower priority. The highest group of the AF11, 21, 31, 41 becomes the lowest scavenger, which means that they all get inverted.
Right. I'm trying to imagine a case where this would be disruptive, where it would be more disruptive than the normal erratic behavior, that performance you get out of the internet today.
Okay, I'll be very quick. Supposing you marked your traffic as AF42 and 41, wanting 41 to be higher than 42, which is a fairly good treatment. When you go through one of these mangling routers, the 41, the higher one, will again get marked as scavenger, and the other treatment would be wrong.
So if the receiver knew that it could tell that it had been corrupted, you would be motivated to complain to the ISP.
Oh, indeed. Yep, so there is a feedback loop, but we want to try and get this deployed as well.
All right, for the sake of the schedule, let's take the one last comment or question here for Gory, and Padma, if you could come up.
Sure, just a quick question. Joe Isaac, NASA Glenn. I have a quick question about if your tool, or if you've been looking at both 4 and 6, if the same bleaching behavior happens on 6 much, or with terms of bleaching the diff server bits and stuff, code points.
I'll take that one offline. There's a lot of different things happen. And yeah, the most common weird treatment, it results from this diff-serve mapping using TOS bleaching the top 3 bits. But there are other ISPs who are actually doing what diff-serve would expect and degrading maybe EF to another class and trying to remark all the traffic consistently. When you couple these two, you get a very large combination of different things happening.
I'll talk to you.
Sure. All right. Thanks a lot, Gory. So next up, we have Padma Bhuma talking about their experiences enabling ECN.
Hello, everyone. I don't know if everybody can hear me.
Take the mic out of the stand.
There you go. Yeah. So I'm Padma Bhuma from Apple. Today I want to share our experience with enabling ECN on the internet. So Apple enabled ECN negotiation on most of the connections from the client side for the first time on iOS and macOS. This is ECN negotiation according to RxC 3168. In iOS 9 and macOS El Capitan, which is like a year old, we enabled ECN negotiation on 5% of randomly selected connections. And in iOS 10 and macOS Sierra, which is the most recent one, we enabled it on 50% of randomly selected ECN connections, randomly selected TCP connections on Wi-Fi and Ethernet interfaces, and also on a few cellular carriers with whom we work closely. This is important because there were some papers and there was data that ECN was enabled by default on the server side, but nobody was using it from the client side, so it's not being used. But since Apple enabled it on most of the connections. Now it's being negotiated. This is a quick recap of ECN benefits and also kind of to summarize what our goal at Apple is. We want to reduce packet loss in the internet. We want to promote deployment of smart queue management at the bottleneck routers, reduce buffer bloat, and as an end result, improve user experience. And there is a draft which really nicely summarizes ECN benefits. So this is the first thing I want to share. After enabling ECN on 50% of the TCP connections on almost every Apple device, we haven't seen any problems reported either from customers or network providers or service providers. So that's really great news, and we're really excited about it. And so that's really the first thing that I want to share here. Now let's take a step back. Even though we did not see any problems reported from the customers, since the internet has middle boxes that might not treat ECN-enabled SYNs or data packets correctly, we think there might be some kind of soft, like performance problems. So Apple, iOS, and macOS have a few heuristics to deal with these performance problems. And whenever a heuristic is triggered, we try to back up using VCN for a limited period of time, which is kind of in the order of an hour or so, and then we retry it again. This is kind of like a strategy, a fallback strategy that we use so we can actually enable ECN and identify paths on which ECN will actually work correctly in the internet. In the next few slides, I'm going to quickly go through 5 heuristics that were implemented in iOS and macOS and discuss them briefly. So the first one is CE marking on every packet. So that's the problem we have seen. It was seen on an ISP in Germany. It was also discussed at a heart surgery presentation in the past. You can imagine what happens if there is a CE marking on every packet. That's like it's always conditioned, right? So, well, TCP comes to a very slow, gets very low performance. The heuristic that we implemented is, since we have both ECN and non-ECN connections, if we ever see CE marking on non-ECN connections, then we fall back to disable ECN for an hour or so. The second point in the heuristic is if we see CE marking on 7 out of first 10 packets on a ECN connection, then also the heuristic is triggered. We have a metric that shows that since like a year or so ago, when we actually discovered a problem, it was actually fixed on the ISP where it was originally reported. And we also see that this problem does not happen on any of the other ISPs in the internet, so which is, again, another good news. The next heuristic we have is for packet reordering. Again, packet reordering can cause performance degradation, even though many OSs have ways to detect and handle reordering, it still maybe can cause a problem. So the heuristic we have is on the receiver side, whenever there is pause drop, we disable ECN for a limited period of time. This is because pause drop can happen because of certain interactions. It can happen when there is reordering. Certain interactions between retransmits and limited transmits, pause drops are possible. So that is a way we detect it. And the second way we trigger the heuristic is when reordering is detected using selective acknowledgements. There's a draft about it. Basically, if we get a few selective acknowledgements, but we get a cumulative acknowledgement before the packet is retransmitted, then that's an indication that reordering is happening. The third heuristic we have is SYN loss. We did not really see any network or middle boxes doing this really, but there is anecdotal evidence that this might be happening for ECN connections. So most OSs, when they send the first SYN, they set the ECN bits on it, and if it is dropped, they send the second SYN without ECN bits on it. We have another heuristic on top of it where if more than 2 successive ECN negotiating SINs are dropped, then we try not to do ECN for a limited period of time. So that is, again, because we just want to avoid the extra RTO that will be caused if we lose the first SIN. ECN is disabled conservatively even if the SIN loss is due to other reasons. This is like the SINs get lost in the network all the time. So, but we don't try to figure out whether it is really because of ECN marking, but we conservatively disable it. The fourth heuristic we have is reset on first data packet. Again, this is not something we have seen in the field. It's anecdotal. The problem is apparently there are some broken ECMP routers that use the IPTOS byte in the hash computation. So what happens is if you have a connection with some packets that have IPTOS bit set and others that don't have TOS bit set, it is possible that they reach 2 different destinations. And then what happens is, you could get a reset from a connection from one of the destinations that is wrong. So the way we detect it is if the connection gets established using a SIN on which there are no TOS bits set, and the first data packet that we send out, which has TOS bits set, triggers a reset, then that we identify as a signature. And we say, if we see this signature on 2 connections, more than 2 connections, then we, again, disable it for a short period of time. Oh, I think I skipped one. Yeah, so the 5th heuristic we have, this is the last one, we have is where connection drop happens after multiple retransmissions. So this is, again, we don't know if this is really a problem due to ECN. Connection drops happen because there is some kind of disconnection in the network, right, for a short period of time. But it is also a signature of, black holing. We don't have any kind of indication that this is happening in the internet, but it is just a kind of a conservative heuristic that we have in place. So if more than 4 successively established ECN-enabled connections fail to send after multiple retransmissions, then again we fall back to non-ECN. I have a few quick points here about the heuristics that I described so far. The first point is heuristics disable ECN conservatively for a limited time, even if the underlying problem is not due to ECN. It's kind of hard to detect whether a problem is happening due to a particular bit on the packet because we don't have the capability to generate our own packets. We have to depend on what the user is doing. So our strategy has been that if we find any problem that could be due to this, we just conservatively disable it. From the data collected so far, heuristics are triggered rarely, but since we don't know whether it's really due to ECN, some of them are also false positives. So the last point is, even though we have all these heuristics, we are not really that happy about them because effectively, we are kind of working around the brokenness in the network, and we don't want to do that. We want to reach a place where these broken middle boxes are actually fixed, and we can use ECN, and everybody can use ECN end-to-end without, extra workarounds. So on this slide, I'm trying to show what we have learned about CE marking in the network. We have a metric that we're collecting from Apple devices around the world. This metric measures how many ECN connections have seen CE marking during a 12-hour period of time. So we have seen that from the United States, 0.2% of reports say that they have seen some kind of CE marking during 12 hours. Even though it's 0.2%, given the total number of reports, it's a reasonably big number. And China, it's 1%, Mexico, 3.2%, France, 6%, which is very encouraging. And really the mind-blowing number for me was Argentine Republic, 30%. That was just amazing. We have close to like 100,000 reports which is, and around 32,000 of them show that there is an ISP somewhere, we don't know which one, in Argentina that's using CE marking on Wi-Fi and Ethernet networks. So that's amazing. The last point that I showed here is marking was mainly seen on the uplink from the client devices, which means clients see CE set on the network and ECE echo back to them. So they see ECE way more than actually CE being set on the downlink. So what that means is there is more congestion in the uplink than there is in the downlink, which is probably expected because of the asymmetric nature of the networks. Okay. So in the next few slides, I'm going to present some performance comparisons that we have done between ECN and non-ECN connections. What we did is we're measuring some of the path characteristics that a device might see on ECN versus non-ECN connections during a period of 12 hours. So for each of these metrics, we have a measurement. One is for ECN and another one is for non-ECN. And the path characteristics that we are measuring are RTT, average, and variance, percentage of out-of-order bytes, which indicates the amount of packet loss in the downlink because the receiver sees out-of-order bytes, and percentage of packet retransmissions, which is lost packets in the uplink, connection drops, and percentage of reordered packets. So every device reports these path characteristics seen on ECN and non-ECN as two separate metrics during a 12-hour period. And then we compared those two because our goal is to see that ECN connections perform no worse than non-ECN connections. And the reasons are obvious. It makes it safe for Apple to use ECN on the network. And it also gives us confidence that it can be used and ECN can be used, and it offers a competitive advantage for ISPs that do smart queuing with support for ECN. The way we are analyzing this performance data is using heat maps. What we're doing is we are mapping this data on a 100 by 100 metrics, where ECN on metric is on y-axis and ECN off metric is on x-axis. I have a couple of samples later on, but depending on what a device reports for a particular metric, for ECN on and ECN off, it falls into one of the cells on that matrix. So each cell has a count of the number of reports that fall into the ECN off, ECN on values as XY coordinates. And then each cell is color-coded using the count of records on that cell. So we're trying to see where most of the records from the world fall for a particular metric, let's say RTT average or out-of-order bytes, and we're trying to see if there is any skew in them.
I think you have a question here.
The question was about Jim Roskin, by the way. The question was about the comment that you thought there was more congestion on the uplink than the downlink because you saw ECN markings dominating in one direction versus the other. Is it also plausible that the congestion points were not marking? And the second thing is, and if your conjecture is correct, have you validated this by looking at packet loss in the up direction versus the down direction and verified that also supports your assertion? Thank you.
No, we don't have a metric to measure packet loss. We do have the out-of-order bytes and packet retransmissions, but that statement was purely based on the CE marking that we are seeing. So we are just seeing 90% more ECEs versus CEs, and that's about it.
It was just very surprising because the downlink would be getting tighter and tighter and tighter, so that's where I would expect to see congestion. And the uplink, maybe I'm going to give you a better answer.
Let me just jump in, Stuart Cheshire. The statement was there was more marking, not more congestion. What that suggests is that there may be a home gateway that is marking CE on upstream traffic when there's congestion, but the head-end equipment at the other end is not doing the corresponding in the downstream direction. So we're not commenting on the amount of congestion, we're commenting on the amount of marking.
All right, I misunderstood your comment. Thank you.
So here I have a heat map It's a 100 by 100 matrix, and the y-axis is ECN on out of order byte percentage, and the x-axis is ECN off. Depending, for instance, if there's a device that sees like 1% ECN on out of order and 2% ECN off out of order bytes, it will fall at like the 2-1 cell. And you can imagine it as a stack of records, and each one is color coded, and I have the color code towards the end. The real heat is in the dark blue area at the top left corner. If you imagine it as a mountain, that's where the peak is. What we're trying to do here is we're trying to see that it's distributed, the heat is distributed evenly for ECN on and ECN off. So there is no, they're comparable. The performance they're getting is comparable. So the y-axis is ECN on and x is ECN off. 0 at the top. 0 at the left. Sorry, you can't see it. So 3 billion reports from the field were used for this data representation. Maximum heat is around 0 to 2% of out-of-order bytes. The report count is distributed evenly or symmetrically along the diagonal, which means we don't see any problem. If there is a problem, we have seen the heat distributed towards ECN on or off. And this indicates that the percentage of out-of-order bytes is not worse for ECN connections than it is for non-ECN connections. I thought of sharing this because it, again, gives us more confidence that, you know, setting ECN bits on packets is not giving us, causing any problems. I have another sample, another quick sample of heat map. In this case, we are comparing the round trip time. Again, ECN on the y-axis and ECN off on the x-axis, and the heat, like the peak of the mountain is the dark blue spot at the top. Again, there is reasonably even distribution of heat for this one also.
Matt, do you have something that you want to inject here?
I wanted to know if you'd made any effort to fingerprint any of these devices, because there was a study a few years ago that showed problems with ECN, and it turned out it was one line of code bug in one vendor's product, which once it was reported, it was fixed. In fact, it was a one keystroke bug, I believe, as I would expect this bug to be as well.
Well, from the client side, it's hard to fingerprint what is on the network because there could be so many things on the network. What we are just trying to do is, given everything that's existing in the network, how is the end user performance affected just because of the marking? So we have ability to kind of drill down a little bit, but not to the extent where we can fingerprint a device on the network.
Does the server side know if the client side heuristics are tripped?
Pardon me?
Does the client inform the server if the heuristics get tripped to turn off ECN?
No, it's only on the client side. So it will not use ECN for the connections that it will try after that. So those are purely client-side heuristics.
Matt, Stuart Church, I want to add a comment. This test is not to some test server run by Apple. This is every TCP connection you make, every SSH.
I understand.
Every time you check your mail.
We do the same thing.
And I'm also not clear, when you're talking about identifying that bug, I'm not sure what you're talking about, because
you could pick any particular anomaly up here and construct, for instance, a custom version of traceroute to exercise it, identify the hop where the problem appears, figure out what vendor, what ISP it was, and track down the bug. And it may be that there's a small number of single line fixes that would actually make things a lot better.
The reason I came to the microphone was the high level takeaway is we didn't find any problems. So there really isn't anything to track down. In the heat maps, we were looking at, is there a bias between behaviors that happen more with ECN or more without ECN? And we ended up that clients that get 2% packet loss tend to get 2% packet loss with or without ECN. So broadly what we found was there's nothing to see here.
Oh, I thought the reordering was ECN related, and that was, that's also one character bug.
Okay, so now I know what you've made. The specific, not the heat maps, but the heuristics we had are rare occurrences. And yes, you're right. In that case, we could try to track down the vendor.
All right, thanks, Stuart. So Pat, why don't you wrap it up?
Yes. So in summary, ECN negotiation is enabled on 50% of connections, but we haven't seen any problems. There's increased adoption. And it's the last bullet point is it's a call for network providers and service providers to think about enabling ECN and testing on the network so it can be deployed end-to-end successfully. Thanks.
Thanks,
Questions?
Ben. Is there a final comment question? Yeah. Yeah. So next up, Tommy Pauly's going to give us at least what we asked for is an update on what he brought to us last year. So one of the things I'm hoping to do in Maprg during its run is get a measurement, and some of these folks are doing continual measurements and coming back and giving us an update. Give it away. Great.
All right, so I'll be quick. So in July at IETF 96 in Berlin, I presented some of our initial data that we had in our betas of iOS 10 macOS Sierra. We started then getting measurements on 1% of all our connections, and we could measure stuff like how often we were doing v4 v6 and how often we saw happy eyeballs kick in on dual stack hosts. As a summary, we saw that about 6% of all of our connections ended up looking like dual stack. We had the option to do either v4 or v6. And of those that were eligible, we did v6 87% of the time, and that we saw that happy eyeballs essentially took effect by having us fall back about 5% of the time. The update is that now we have data from not the betas, we have data from the real deployment. So we have about 5 months of that data, and we are capturing in this rather than 1% of all connections, just because we have a lot bigger scale, we're doing 0.1% of all connections. So what do we see? So I have 2 snapshots shown up here, one from October 2016 and one from just this month. Overall, we see that of all connections, about 90% in both cases look like v4 only hosts. That either means that we're on a v4 only network, or it means that we're on a dual stack network, but the DNS only returns us a v4 address. We saw initially 9% of dual stack hosts, which means we're on a dual stack network and we get back both addresses. The surprising thing and the cool thing is that now we see in this month that we have about 3% of connections look like v6 only connections. And that means one of 2 things, either that we are on a NAT64 network and we are only being given back the quad A record, or we are on a dual stack network and somehow we are getting something that is only giving us back the quad A record. I imagine in large part this is going to be NAT64 networks, but it shows us that we actually are seeing this deployed. So here's a actual time graph of this. So we see that at a certain inflection point, people started turning on NAT64 networks. Various networks are starting to do this. So we do see an actual rise in the number of connections that to us seem like v6 only connections. There is definitely fluctuation in that. People are turning it on and off. So we see the numbers go up and down. But the interesting thing to note here is that the actual total number of v6 connections doesn't really go up, but they are changing in nature from things that were racing happy eyeballs to being more things that are kind of pure v6. When we do look at happy eyeballs, this is trying to measure out what actually happens on these connections. So what we're looking at is the percentage of all connections that were eligible to do happy eyeballs. So these are things that were dual stack connections. So again, about 80% of the time, v6 just outright wins. We try it first, it connects, no problems. Then there are 2 other possibilities, really. One is that for some historical reasons, we have noticed that v6 is being slower or has failed altogether, and we end up trying v4 first. and that wins. And the other case is that we try V6 and it has to time out and fall back to V4. So I want to zoom in just on that part because that's fairly interesting. So we notice that, I mean, they're fairly erratic over time. We're just looking at this data now, so we don't quite understand what causes it, but we do see that there are inflection points of the changes around the times that we know that networks were changing their deployment of NAT64. And so that's taking the pool of dual stack connections and changing the nature of that. So it's just interesting to see that, especially now, we are seeing a higher percentage of the V4 connections on these dual stack hosts being cases in which we try V6 first and are falling back. That would seem to indicate that the kind of the differential of the performance is getting closer, because if you have a larger gap between V6 being broken or very slow, we'll end up doing V4 first. Whereas now it seems like the trend is that we see more cases in which they are very close and we have a true race. And then some of the time V4 wins, but not often. All right, so just to summarize that, the overall split we see between V4 and V6 hasn't really changed all that much over our measurement period, but the nature of the V6 connections has changed. Shows mainly NAT64 deployment, or people are suppressing A queries, which I doubt is happening. And then we do see that Happy Eyeballs has fluctuations. We'll continue to measure this, see how that changes. I haven't really seen any other measurements of Happy Eyeballs because this is something that's very client-side specific. It's really hard to understand this from the network perspective. So we'll continue to monitor that and let you know if there's anything interesting. And it's also interesting to note that as we see changes in the V6 only connections in the NAT64 deployments, that is affecting which networks are left doing Happy Eyeballs. And it could be that a higher relative percentage of those have more V6 problems because they're not the ones that are going aggressively towards V6. And that's about it. Questions?
Have you done any experiments to try and gauge the quality of experience between dual stack ISPs and IPv4 ISPs that are running carrier grade NAT, for instance?
IPv4 only?
Right.
So we have, I mean, at this large scale, we have measurements of the latency for connections and for TLS handshakes and stuff. So we can break it down that way. We don't have a metric for the higher end user experience other than the latency towards connection.
So I have been, I've been dual stack for a long time.
Yep.
And I've been in a hotel that, not here, not recently, that was carrier grade NAT, that had the property that about 10% of my connections outright failed. Because the port space was blown out in the NAT, it wasn't big enough. And I suspect in that same hotel, IPv6 would have been excellent because of your circumstantial evidences, but it wasn't available.
Got it.
And so, in fact, if I had had a dual stack host, I would have been had a much better network experience than somebody who was IPv4 only.
And in measurement, would that lead towards failed connections or just badly performant connections?
Unfortunately, the symptom is failed connections in a series of otherwise successful connections. So it's kind of a subtle symptom.
Right, and so we do have metrics on failed connections, but it's hard for us to differentiate between a case in which it was a dual stack network and maybe it was just a V4 only host. We don't know.
I've been advocating somebody to try and do this experiment for a long time because I believe it to be the case today that dual stack, because of the prevalence of dual stack devices, that ISPs that are dual stack actually do much better in the quality of experience than IPv4 only.
Yeah, I imagine.
Thanks for doing this and publishing it. Oh, I'm Mark Townsley. Can you go to slide 4? What happened in February?
Deployments that choose to try out NAT64 may change the scale at which they deploy NAT64.
Well, the NAT64 didn't change much. I mean, even the IPv4 only.
I know.
And the duals, it seems like something happened. So do you have? Like,
I think it's deployment of networks and their changes. I don't know the details of that, and I can't really comment too much. But yes, it's something that we want to look into. Yes, right. The total did fluctuate a little bit around the December timeframe, so that could account for a little bit of the bump. Yeah.
I suspect this is just a small number of big deployments changing knobs.
Yes.
Thanks, Tommy, for bringing this to us. I was interested in, during this time series you have both in this slide and in slide 6, how do you track what's going on in your implementation during that time so we can find the effects of the change in the happy eyeballs implementation, its effects on the measurements? And also, does anyone know, open-ended, I'm going to go back up there, but does anyone know of an effort to characterize how many different happy eyeballs are out there, and what do you think we should do as a community to start understanding the heterogeneity there with the implementations?
Right. So during this time frame, there is a shift in which we have a beta, actually release that just came out today or yesterday of a new dot update. So we can internally break down the numbers between that time. So around the January timeframe, we did have a new beta with a couple changes in it. We didn't see a significant change in that. But yes, as far as the happy eyeballs, you can come to V6 Ops. David and I have a draft of trying to update happy eyeballs to share the approach that we do. I'm aware of this implementation. I mean, Google has their approach. Firefox.
Okay.
Can you go to the last slide? Sorry.
No, I was just going to say, let's just do Lorenzo quick, and Tobias, you can.
So the last bullet point, you don't race V6 with NAT64, right?
No.
Right. So that's what that last point says, I think.
Yes. Well, essentially, as you get NAT64, you don't have racing,
But
and so you're taking that out of the pool.
But you could. Now,
Well, so no,
whether you
we
should
will-
or not
we
is a
will
different
race-
question.
We will race the various V6 addresses. We fall back between any V6 addresses we have. In measurement, we don't see any significant way of doing that. We could consider actually racing the things that we know are synthesized V6 addresses versus native V6 addresses, but that's getting tricky.
So racing the NAT64 versus racing V6 and NAT64 is very different in your implementation than racing V6 and V4, right?
Yes.
Right. So I think whether you could or you should, probably, like I would say from a V6 perspective, you shouldn't race NAT64 and V6, but from a user perspective, maybe you should. But I think that's what that last bullet says.
Yep, exactly.
All right, thanks, Tom. Okay, so let me find here. All right, next we have Tobias Fiebig visiting us to talk about their IP6.ARPA efforts to scan the V6 image.
So good morning, everybody. Like this.
Yeah, you can pick it up there if you'd like, and just hold it in your hand, and we'll be able to.
Better? Okay, so good morning. I'm a PhD student at TU Berlin with Professor Anja Feldman, and this is joint work with a couple of researchers from UCSB. If we are looking at how IPv6 is currently evaluated, we find various good works, among others from Dave Plonker, which are usually focusing on using a vantage point, which is in some form proprietary, similar to the earlier work just presented by Apple. There's also work by Cis et al., which is already using DNS, but it's basically just using any queries and double PTR lookups to identify quad A records and thereby IPv6 addresses. And furthermore, there's Gasser et al., who is using an IXP to actually read IPv6 addresses that are passing by on the Internet Exchange Point. We wanted to find a technique which enables us as researchers to identify, measure, and investigate IPv6 deployments without having the need to access a dedicated vantage point. First credits. This technique was suggested by me by Peter van Dijk, which is employee of ParDNS, I think. The technique is already documented in RC 7707 and heavily funds on the NX domain semantics as put forward in 8020. So let's quickly recap IPv6 and IP6.ARPR. If we have our little IPv6 address here, the basic algorithm to get the IP6 ARPR entry is reversing it, exploding it, and putting dots in between the nibbles and appending IP6.ARPR.
Tobias, could I ask you to speak up a little more, maybe like a little bit?
Okay. I'll try my best. The technique we're using is, if you're looking at the DNS tree, you basically get, following RFC 8020, NX domain if you do not have any nodes below the node you are querying or at the point of the node you are querying, which basically means that you can prune your walk of the tree. So if you receive an NX domain, you do not explore that path in the tree anymore. Those where you receive no error, you descend up until you have hit the full length of IP6.ARPR, which is 32 nibbles. So as I said, the technique in itself is not new. RFC 7707 already mentions it as a technique to explore single networks. Van Dijk also did some preliminary studies on this, and he also provided a brief Python implementation we started to use. However, in practice, there are a couple of civets you have to keep in mind if you want to apply the technique globally. The first one is that technically the search algorithm is depth first, so we actually decided to introduce a mixture of depth and breadth first search by parallelizing over 4 nibble steps, which means that we first enumerate all bases we find, like from IP6.ARPR up to a depth of 4 nibbles, and then for each of these we again enumerate 4 nibble steps deeper. Then for each of these again, basically making this a mixture of breadth and depth first search. Another thing is dynamically generated zones or auto-generated zones. If you're a large ISP, you probably don't want to set IPv6 records for all IPv6 addresses you're applying to your customers. Hence, usually the zones are dynamically generated, which also means that the DNS server knows for every PTR record in that zone that there is a record, which ultimately leads to you enumerating the whole subtree. This is not really beneficial because for even a small network of a /64, this is 2 to the power 32 times the address space of before you would be enumerating with this technique. So we actually deployed a relatively simple algorithm. We checked if all suffixes for a given base, which only contained 1 character, were present, and if 3 or more of these were present, we excluded the base as dynamically generated. This sounds relatively, well, oversightful, but in practice it proved to work actually pretty well. Okay, this slide would normally be a slide where we just try this, but sadly I do not have a mouse to paint on this. So what you actually see is the black path you will be taking if you only receive a no error for an NX for the f.ip6.ARPR query. Then you receive only no error and NX domain for the others for 0.f.ip6.ARPR. And so forth. So on the next level, you only receive no error for f.0.f.ip6.ARPR. In addition to just enumerating starting from IP6.ARPR, we also added seed sets. So we aggregated a GRT view, so global routing table view, from route views and the RipeRIS project, and used the prefixes converted to their IP6.ARPR representation as seed sets for or scans. You can also integrate other possible seed sources, and something you have to keep in mind is that if you use the 4 nibble step approach that we've been using, you will receive seeds which are sufficiently significantly longer. So, for example, /84s announced in the GRT have to be treated in some way to be applicable still if you are only enumerating to that of 4 nibbles. We decided if we are encountering something which is longer than the nibble size we want to enumerate to, that we would just crop it to that length and also add the original seed back to the data set. So let's get a quick look at first insights. In general, with these scans from a single machine, we found around 5.5 million records in IP6.offer. We are currently running a new set of experiments with a more distributed measurement setup, which seems to be a lot more successful. But for the first experiments, we actually found, does this have a pointer? No. Anyway, we found these, this was the enumeration from /64 to /128. We found a lower bound, which is basically the 16 queries we do need, plus an additional one for, additional 2 actually, for suffixes, so hosts in /64s that end on : : 1. So on the lower bound of that white space there, you actually see all those structured networks. Also the right from your side arm of that plot are technically all those structured networks, starting from 0, just incrementing their host names. While on the left side you have all the pretty unstructured networks. Well, technically and wiki-wise unstructured networks. For example, being based on UI 64. We also performed a couple of case studies. So with this technique, you can actually look into the numbering plans of operators. So this is an SaaS provider, which actually has a pretty rigid IPv6 PTR assignment. So you can see that they are actually having 3 regions, signified by 3/32s. In those 3 regions, they're using single /48s for varying functions, and they're allocating /84s and /48s and hosts within them, incrementing starting from 1. The little outbreak at the what is that? 76th nibble is, by the way, their distinction bit for no, at the 48th nibble. This is the distinction bit for transit networks. Due to the well, better opportunities to build structured networks with IPv6, you just have more space and more networks to put your segments together. You can also generate topologies far better from IPv6 PTR entries than from IPv4. And we actually did this for a couple of networks. So based on how the networks are naming their hosts, this is for a network which named all hosts, even though they are in different networks, as routers, for example, the same. It's relatively easy. Other networks, like, for example, the SaaS provider, also encode additional geographical information in the PTR records, which also is helpful. Mitigation, well, it's pretty hard to mitigate this without violating RFC 8020, but there's a couple of tools which are applicable to all the zones, to all their name servers, basically working with wildcard records. So conclusion was you can reject, but you cannot hide. There's a tool chain publicly available. I'll also later post the link in the Java. There's an upcoming publication at the Passive Active Measurement Conference, and there's also a full-length talk available online under that URL. Thank you.
Great, thanks Tobias for bringing this to us. and I'll be checking out the paper this week. Are there questions or comments? We got 2 minutes.
Ben Schwartz, Jigsaw. Would you recommend that a cloud provider take any action to try to mitigate this? So, for example, would you recommend that a cloud provider register reverse DNS records for their entire IPv6 range ahead of time, essentially, in order to avoid revealing which VMs are actually active?
I personally believe in open security. So if your topology is providing an attacker with an advantage, it's already going wrong there. But that's my personal opinion. There are others who are recommending to keep your topology hidden. I disagree with that. But if you're believing in that train of thought, then you should hide your DNS, well, reverse DNS.
Thank you.
One last question.
It's more of a comment, Tim Chan. So I happened to supervise a PhD recently that was looking at architectures for intrusion detection in V6. And one of the demonstrators he used in the thesis was to detect this type of walking with various pattern matching and intrusion detection systems. So if you're seeing a constant walking through your zones, you can detect that and block it if you wish, as opposed to just direct lookups of specific items. There are ways to do it, and I would certainly probably be quite keen to deploy that type of thing at the edge of mine.
So you were suggesting just detecting basically the
It's detecting it, yeah, as a type of scan, just as a traditional port scan. It would be like detecting the reverse, the walk through the reverse as well.
That is technically true, but on the other hand, we also see problems in rate limiting authoritative requests for reflection attacks.
Yeah.
So thank you.
All right, thanks again, Tobias.
And please remember to say your name when you're in the mic line.
All right. Yeah, so my name is Giovanni. I'll be presenting this work. It has been conducted by, us, I work for IDN and some colleagues at TU Delft and the National Cybersecurity Center, all in the Netherlands. So just before I start, let me get a sense of here of the room and how many people are familiar with Let's Encrypt. All right, got a great crowd here, and I apologize if you already attended the IEPG meeting on Saturday, because it's the same presentation, but well, let's get started. So before I start, I just wanted to have a disclaimer here. I'm not affiliated with Let's Encrypt. None of us are, so we cannot respond for them, right? I'll try to take some questions about them. If I don't know, we better talk to them. But if you want to support them, if you like their cause, just reach them out on their website. All right, so this guy basically has shaken the world in internet security, Edward Snowden, after his revelations. And there's a lot of distrust and fear and panic, but it was also an opportunity to improve security, to deploy more crypto. And we have seen a bunch of reactions here in the IETF, on vendors, on cloud providers. So we also have seen over the years, and here we collect data. It's not us, this is like public data from telemetry obtained from Firefox and Chrome, that currently more than 50% of the web pages that the users experience are actually encrypted. And they collect this data anonymously provided by the users that, so we can get all this data and those references in there. But 50% is a good number, but it's not quite good yet. We need to improve on that. And one of the problems with web encryption, and I'm going to be singled out here in web in this case, is that for having that, you need to have a 509 certificate. And before Let's Encrypt, you had to buy one of those. They cost money. They were complex to deploy. It was not that straightforward. So there were many small websites that have little incentives to deploy those, especially if you want to do that at scale as well. So what Let's Encrypt aimed to do was like, all right, let's try to tackle those problems. Let's first give it away for free for anybody, the certificate, so you reduce cost down to 0. And the complexity of, going to a website, asking for a certificate, buying, deploying manually on your server, what they did, they did a protocol, actually is being currently standardized here. Reference number 4 here, the ACME protocol. If you're interested, join the work group. And they develop a client too, a chatbot, which anyone can use to automate those tasks. So that's pretty much the proposition. That's what they did. Now, this leads us to our work, which is we try to address research questions like how Let's Encrypt has performed the first year of deployments of issues of certificates. Are they really democratizing encryption? And that's what we do in this work. We use, of course, measurements. That's why you're here at Maprg. We analyze the issues of the certificates for the first year. We show adoption from various angles as well. And we also cover the lower end cost of the market. That's the thing we're more interested in. So before I start showing the results, let me show our methodology. So what do we do here? We cover 1 year of measurements, as I said. So when you issue a certificate, you can issue as well for fully qualified domain name. For example, for a.b.c.d.com. And what we do in this work, we normalize this into just the second or third level domain form, like that in this case would be d.com for counter purposes. So we obtain those domains that have the certificates from the certificate transparency reports. You can download them from here. We also need historical mappings from those domains into A records, therefore IP addresses. And we use those mappings using the Fairsight DNSDB. It's just a passive DNS global collection that maps those domains into IP addresses. We are also interested in observe, and on the box, yep, which organizations are using them. So some of my colleagues have developed a methodology on that before, reference number 8 here, and we use like who is data, maximize UIP. And we have a small case study for .nl because we had access to registration data on that, but I'll be covering that. So these are the main data sets we use. Now, this is public information, but I wanted you to focus first here on the growth of Let's Encrypt. So from September 2015 up to September 2016, roughly almost 10 million domains were certificates have been issued for domains. And I mean domains here like fully qualified domain, in this case here, sorry, fully qualified domain names, almost 10 million. If you normalize them, it would be this domain curve here. We would have roughly 4 million almost, so you would have 2.5 certificates per second level domain. And if you compare those numbers with regards to the percentage of the coverage of DNSDB in our data set ranged from 121 million domains per month up to 250 or 210, I'm not sure, it's in the paper. You can see like 2% by September 2016 of the domains seen on DNSDB were actually had Let's Encrypt certificates issued for them. We also show, so we wanted to address the question, who is actually using this thing? And turns out that 98% of certificates are actually outside Alexa 1 million. Well, Alexa 1 million is just a small sample of all domains that exist on the internet, but are the kind of wealthy ones that would have the resources and the technical skills to deploy those. So it's a good news that they are, you're reaching actually people who are not in Alexa 1 million. But it's also interesting to observe that Alexa 1 million domains, for example, they also use Alexa Encrypt in their own subdomains. Let me give you a data point here. So if you get like Alexa top 1,000 domains, and if you go to September 2016, you would see like more than 15%, roughly 20% of them have actually at least one Let's Encrypt certificate issued for one of their subdomains. Because it's cheap, it's for free, and you just do it automatically. So it's a good thing as well. It's not only like the lower end, also like the ones that have more resources are also using. We also we got these domain names, we map them into IP addresses, even then later we map into organizations to see actually who is using that. And this is a graph for 2015. And you see like here, these are the number of organizations on the x-axis here. We have 60,000 organizations by November 2015 using Let's Encrypt. And this is the number of domains, normalized ones. And you see there's a spike here. This means that one organization only has issued a bunch of those certificates. And if you go now to September 2016, which is our last month of analysis, you would see like there are 3 major spikes here. And what do they mean? That mean that 3 organizations are actually responsible for most of the issues of the certificates. You see like 47% of all Let's Encrypt certificates were issued by 3 organizations. Their major host providers, I think one of them is OVH, a French provider, WordPress as well, and Shopify, if I'm not mistaken, is in the paper. And that shows that automation works. What does that mean? because if these host providers they want and they decided to automate for all the clients, for everybody to have encryption, they can do that very easily. And that's what these three guys have done here. So automation works and makes it easy for this complexity. We are also interested to observe which segment of the market would actually using that. And of course, so if you break down the certificates into the markets, it's like, I don't know, CDNs, ISPs, hosting, order, parking, whatever, you would see, of course, web hosting. That's no surprise because, well, these certificates are mostly used for web. You can use them for other things as well, but it's mostly for web. So in this sense, there's no surprises. But if you break down the hosting industry into like shared hosting and like dedicated hosting, shared hosting typically is like mom and pop stores, is small websites that you actually pay a little fee and then everything is virtualized and you share in the same IP address with various the websites. So just make a little bit lower cost. And there is a paper that my colleagues have developed this methodology to classify that. So you use that in this study. And turns out that by September 2016, the far majority of the certificates were issued for the shared hosting. And since the shared hosting is the lower end cost of the market, it's an indication of like how Let's Encrypt is democratizing this access to certificates and encryption. We also were interested in observe how many of the certificates were currently and were actually correctly renewed, because Let's Encrypt would issue a certificate for only 3 months. And if you don't renew that, it would expire, we would have problems. But they also cover that in the SATbot too. So it's very easy to renew. And we did some analysis here, and we showed that actually survivability analysis, the most of the certificates are correctly renewed, which is a great feature for the tool. We're measuring that people are really doing a good job in here. There's more on that in the paper. If you want more details, how we did that. And that's, I'm going to move now to a case study that we have for that now. I work for them, and then we have access to registry information. That's the only one I could pull data from because it's hard to get this sort of information. So I wanted to know, the question that I wanted to know was like this. So they're issuing the certificates for domains, but I wanted to know if these are covering actually new domains or old domains. Because if a hosting provider can, let's say, change the interface and put a button there when you register a new domain and say, hey, you want an encryption for free? Click here. But what about the old domains? So the only way I could do that that I had access to was the data set I have in my fingertips. So what I did, I pulled all the now Let's Encrypt issue domains, certificates, and I measured the ages of those domains that were actually now certified by Let's Encrypt. And turns out most of them are very old. So the median age is like 4, 3, depending on the month, years. And the third quartile are more than 10 years for certain months. So what does this mean? They are covering domains that haven't not been used, probably not been used in encryption, and they were very old, so we're covering ground that hasn't been covered before, which is, again, great news for democratizing encryption. And another point, another interesting thing you might want to be interested is like, okay, they issue certificates, they are doing this great job, there's this tool and everything, but what about deployment? Are people correctly deploying those certificates and their services? And this is a very tricky actually question to answer because these certificates can be used for various applications. It's mostly web, typically. But you can use them for other applications. You can use them only internally in your company. So it's very hard to have a precise measure here. So what we did, we just chose like 25,000 domains. They were certified by Let's Encrypt. And we tried to probe one application only, web, HTTPS. And you download the certificates of them. And you see actually if they're using Let's Encrypt. And the bottom line here is like out of 25,000, almost 16,000 were publicly available websites correctly deploying Let's Encrypt. So personally, I think it's a good number, but there are some of them that had some errors or some domains probably expired here. They had no records anymore. But this shows an indication that people are correctly deploying this. We need actually to extend this to probably all the domains issued by Let's Encrypt. That's also future work. Yeah, so that brings us down to the conclusions. So my understanding, in our understanding, Let's Encrypt has been a success story. It's a good thing for everybody, for the community, for the users. In our understanding as well, they have been democratizing encryption by covering the low cost end of the market, shared hosting. But don't forget the big players are also using it because it's easy and it's for free. And one of the lessons that we have to take as a security community is that automation works. And if you automate and make it easy, it's easy for this hosting providers to deploy to most of their clients. Sorry. Another good news is that, well, majority of certificates are correctly being renewed after the first expiration, the 90 days. So yeah, they are doing a good job in the sense of democratizing encryption. And future work, we want to, of course, extend the measurement period. In this paper, we only cover the first year of issues of those certificates. We also want to do better scans to cover the entire domains and see like what is actually the numbers for the entire data set that are being deployed. And one interesting case we have seen recently, a lot of, let's say, abuse on those last domain certificates, meaning that people issue certificates for domains that would include, for example, PayPal, .com, for example. So we now also should take a look at that. And yeah, these are my contact details. If you like, there's a paper on this URL. Yeah, questions?
All right, thanks so much, Giovanni. We're going to be on time if we take 1 or 2 questions. So I guess Lorenzo goes.
Lorenzo Cludi. So I think, I mean, I am a user of Let's Encrypt. So I think it's great for users. It's also great for the NSA because it means that nobody else can see your traffic except somebody who has essentially legal authority over Let's Encrypt, which is a US corporation in San Francisco. Now, I wonder how I wonder if anyone's thinking about the tension between the natural fact that there's like going to be one obvious, like there's clear economy of scale here, right? It's easy to use Let's Encrypt than any other player, right? But on the other hand, you've got this situation where one jurisdiction basically can see all the world's traffic and nobody else can see it. So it's kind of changing the playing field, right? Before an ISP could snoop on your traffic in one country, and now only the US can snoop on your traffic, right? So I wonder if anyone's thinking about this, if there are any parallel efforts, like as a European, right? You might know of any of these. Because you know, if there was a European one, I'd prefer to use that, but there isn't. So I wonder if anyone's talking about that.
That's a great point. I mean, we didn't cover that in the paper. That moves in more into policy, but I would love to hear opinions on people on that.
Sure. So I'm also just a Let's Encrypt user, Ben Schwartz from Jigsaw. But Let's Encrypt is, first of all, they don't hold private keys for the SSL certificates. You hold the private key, and you only expose to them your public key. And they are bound by the certificate transparency system. So if they fraudulently misissued a certificate, that at least could become public knowledge, and in a way that's irrefutable and traceable. And there hasn't been any evidence of that. So I think it is a fairly safe system as far as maintaining the integrity of private keys. They are vulnerable to, because they're domain validated, they are vulnerable to a certain class of very powerful man-in-the-middle attacks. But in order to execute that attack, you need to be able to permanently intercept both Let's Encrypt's connection to the server and everybody else's connection to the server in perpetuity. And it still is potentially detectable if the server operator checks the certificate transparency logs.
What about the fact that the automation runs on your machine? I guess kind of that's also another one of the double-edged swords, right? The automation runs on your machine and can configure a cert. So potentially it could, it has the private key. So yeah.
That's true. Let's Encrypt could serve you a backdoored cert bot.
Yeah.
That would be certainly a very powerful attack.
All right, thanks again, Giovanni. And I think that's a great topic, and we'll focus after that.
I just say this is not the focus of the work, but it's a very interesting discussion.
So next up we have Rolf Winter presenting some work they've done, and I think it's published, right?
It's published, yeah. And there's an RFC now and an internet draft, which is the last call. Okay, and so today I'm going to talk to you about how broadcast data reveals your identity and social graph. And when I say broadcast data, I also mean multicast data. So everything that's sent by a broadcast or multicast can reveal that. So we did an experiment, and the idea was fairly simple. We put a device on a network and listen to everything that is being broadcast and multicast on the network. And then, well, we wanted to know if there's something that particularly pollutes the network, or if there's data that's interesting to look at, and that's what we did. We had 3 locations where we did that, and you should be aware of this because we did it at the IETF in Yokohama. And we tried to do it in Prague, and there was a lively email discussion around this, and we got private and public comments, and some of them were kind of scary. We were accused of violating basic human rights with this experiment. We were in violation of the EU data protection law. That was actually correct if we would have done it the way they understood it. And we did it in a lab. So in the lab, we had a controlled environment to actually see what we are looking at in the wild, so we can do actually data protection. And our main test bed basically was the EDROM network at my university. So we talked to, I'd say, about 30 lawyers in the process of doing this experiment, because German data protection law, I think, is one of the most strict data protection laws on the planet. And that was very difficult for us because we wanted to actually look at the data, but we weren't really allowed to look at the data and store the data. And we got a lot of lawyers involved that helped us with this. And we could, in the end, do it in a way that is preserving the privacy of the users on the network. I'm going to talk a little bit about this, but not too much. For the IETF, the 39th meeting in Prague, we couldn't resolve it in time. So that's why we did it at the Yokohama IETF meeting, where also the legal framework was a bit more favorable for this experiment. So if you're a German speaker, there's a publication about the legal aspects and, for the German jurisdiction has been published. We got a 30-plus page statement from a lawyer on this, which I don't fully understand. But if I can give it to you if you want to. So it turned out we needed to make every personal identifiable information invisible by encrypting it, hashing it. So it's not reversible. So MAC addresses, IP addresses, and host names were hashed for this experiment. And we needed a trick to do an analysis on this, but one more on this later. In order to not do something wrong, we selected the protocols we looked at very carefully. So we didn't look at everything, but on a number of selected protocols that we know. So we know what the content looks like, so we can actually preserve the privacy of the data. And we weren't allowed to store raw data. So this is, we did it for 6 months on the EROM campus network, obviously. Gave us 60 gigabytes of data. There was up to 1 gigabyte of broadcast and multicast traffic on the network per day. So you can see down here, there was Christmas. There was hardly anybody at the university, a few were. And so that's on average 215 megabytes of data, just broadcast and multicast data on that particular network. And that was actually kind of interesting, just to get you a feeling, to get you the feeling of what the data looked like. We saw 35,000 MAC addresses on the network. Some of them were garbage because I think a student did a really weird networking experiment in those 6 months, but we could filter this out. And these are the main contributors to the traffic. It's MDNS, SSTP, LLMNR, it's NetBIOS over TCP/IP, and the desktop client of a very popular cloud storage provider. So that was interesting. So as an IETF person, you should know MDNS and SSTP, LLMNR should be known to you, but this application looked interesting. So we looked into this, and it's basically used to do local data exchange. So the cloud provider doesn't have to exchange the data between two people in the same LAN over the internet, but directly. So the authentication, everything is done over the internet, obviously, but the data exchange later on is done over the LAN. It's good for the cloud provider. It's good for the user because it's a fast data exchange. What it does is every 30 seconds, it broadcasts a number of packets. And there's two things interesting in those packets. One thing is a unique identifier for the installation of that particular desktop application. And the other thing is unique IDs for all the shares. So for the folders and documents you are sharing, it's unique identifiers, but nothing else. So you can't read what the person is actually sharing, but you see unique identifiers. Yeah. So the host end actually is kind of bad, and we talk about this in the internet draft, because a lot of people now talk about MAC address randomization and IP address randomization. But if there's an application out there that broadcasts a steady identifier all the time, you can basically stop working on MAC address and IP address randomization. So there were on that network 2,500 odd installations of that application with over 9,000 shares. And the question is, can you draw a graph from this? So you can draw a graph of data being shared by devices, and we did. So this is just one example of what we did, and the black dots here, those are the shares. So this is the data that is being shared, and the green ones are people, or they're not people, but devices sharing the data. It would be really interesting if we could make those devices into humans, so who is actually sharing the data. So then we went on and looked at host names, and they're actually kind of interesting because they contain a lot of PII. So it turns out that, so we found 7,600 host names. Some other protocols use host names to distribute data. And you can read the language from a host name. So the first example here says iPhone font John Doe, which basically means he's a German speaker because there's a font. And we had multiple languages in there, so iPhones readily give out the language of the person owning the device. The device vendor is very often known, the location or the function of the device. But the most interesting thing for us that we found was very often it's login names, nicknames, and the real names of the person. So that's interesting. We weren't allowed to look at this, but it's still interesting. So we hashed the names, in particular the host names. So we didn't have the clear text names anymore. So wouldn't it be great if there's a database of people and names that you can find, hash those two, give them the same key, and then you can match the values. So if you find a value in a host name, and you find a value in the database and they match, then you know this is first name or last name of a person on the campus, and then you don't have to look at the raw data. So that would be great. And the LDAP server of the university was accessible from within the network. We crawled it. We got 8,400 users. We got the login name, the first name, the last name, the department, course of study, the status, so if they are a student or professor or staff, and the last time they changed their password. So actually that sounds stupid, but this way we found out in which semester they are, because people never change their password. You laugh, but it's true. So this way we got 4,500 unique last names. So if I find a hash of this thing, then I know the person because the last name is unique. We found 1,300 unique first names. So if you name your device up with your first name, doesn't mean you're secure because there's a lot of people with a name. No, in our population, 1,300 people had a unique first name on the network. And then we compared those names to the host names. So this is what we found. And this is all lower bound because we lose a lot of information through our hashing process. So there's typos in host names, and sometimes you use a nickname, and the nickname is not in the LDAP. So this is a lower bound of what you actually can find out about people. So in those host names, 2,900 contained a first name. So a significant fraction of the devices on the network as a host name have the first name of the person owning the device as part of their host name. And 500 of those matched uniquely. Still 930 last names were found in host names, and there you have a probability of 50% being unique. And interesting was that 293 people actually used their full name as part of their host name, which, well, it's still a 90% match because there's a lot of popular host names, last names and first names being used in Germany. But this was for our population, but that was very interesting. So now we basically light up this graph. It's not devices anymore, but now it's people. So we know who is actually sharing data with whom. Right. And on the IETF network, we use the attendees list for this. So you are safe. We adhere to German data protection law, even in a country where that's not necessary. So everything is safe. And since then, broadcast has been switched off. So it's not as interesting anymore on the IETF network. So you can do this, but you won't see broadcasts anymore. For performance reasons, though. Right. So then since everything was hashed, we didn't really know whether we actually found the ground truth. We saw hash values, compared them, and they matched. So we went into a lecture. Well, we actually went to multiple lectures. And then we put an access point there. So EDROM sucks at our university. So now I said it. It's on record now. EDROM sucks at our university. The wireless sucks. So I put an access point into the lecture hall and said, okay, I explained the experiment and said, you can connect to this access point, internet's going to be great, and we're going to store all your data in clear text. So if you connect to this access point, it's consent that we are actually allowed to do this. And we asked lawyers whether it's okay, and they said yes, it's okay, as long as there's an alternative way to access the internet. If it's the only way to access the internet, it's illegal. And if there's an alternative way for people to access the internet, it's actually legal. Yeah, it's interesting. So, so somebody live collected the data, and then it did like a little magic trick. And a student of mine was there, and then he sent me hints via Jabber. And so I went to a person. That was the only person with a Lenovo laptop in the room. And I know her first name, her last name, and her nickname. So I could single her out and say, okay, is this your, I told her her name. And I said, your friends call you this. And she was shocked. She was, how do you know? How do you know? And we did this a couple of times, and there's always people you can find. So, okay, somebody in the room speaking Italian, his first name is Bla, his last name begins with the letter R. And it's very, very easy. There's more you can do. So we also looked at social networking profiles to find out more about these people. It's kind of like stalking what we did. We crawled the timetables of the university to figure out where they are. We knew they were online because we could see the broadcast, but we could also knew where they are based on the timetable and things like that. So it's kind of scary what you can do only by listening into broadcast and multicast traffic. That's all you need. So you don't need a special position in the network. You don't need to hack the router to see all of the traffic. You just have to become part of the network. That's it. So what can you do? So, oh, and by the way, on the IETF, we picked the IETF network as a reference network because it's networking professionals. These guys have invented the internet. Of course, they would never name the device after themselves. Guess what? Okay. So please Google now how to change the name of your device. If you use an Apple device, there's 3 names actually you have to change. But you should never actually name the device after yourself. It's a really bad idea because I can find out lots of things about you. You could switch off broadcast and multicast, but that's just stupid because the features that a lot of applications implement are very, very useful. So you shouldn't do that. You can, and at the IETF on the wireless at least, broadcast is switch off, but for performance reasons. But you should really not name the device after yourself. And there's an RFC out there, 8117, that talks about the stupidity of host names, and there's another one coming up that gives some advice to broadcast and multicast protocol designers to make better protocols. All right. That's it. Do you have questions?
All right, thanks, Rolf. And you guys are doing a great job of making me honest by making sure there's enough time for the last 2 presenters. We have 20 minutes each for the last one. If there's a question or comment for Rolf, we could fit that in. Is the last speaker Will Scott here? Great. Okay. So let's take this question or comment.
Tim Chang. Yeah, I think this is really good work, and I've seen some of the other stuff that's come from your group as well, which is really good too. I think as a user, I think when users have got a new computer in front of them, they're just asked to name the computer. The last thing in their head is when they've got that type in a name for your computer, that if they put their name, which is probably the default on, I think, Apple devices, for example, then they don't think about that. In terms of making things better, I'd just like to a pointer to DNSSD this afternoon at 4:40. There's talks by Christian Huertema on privacy for DNSSD service discovery, and also a proposal for doing device pairing with privacy as well, which I think helps with the type of thing you've been talking about. So if people are interested in that, come along 4:40.
Thank you. Thanks again, Wolf. All right, our penultimate presentation is Marcella Hastings, who's bringing wikis remain widespread in network devices to us from the presentation at IMC. And I'm particularly happy that we record and IMC didn't this year, so this will be available online.
Great. Thanks so much, Dave. Yeah, so I'm going to be talking today about some work with my co-authors at the University of Pennsylvania, and I will dive right in. We're running on time. In 2012, 2 groups of researchers independently discovered a vulnerability that allowed them to factor 0.5% of RSA keys being served over HTTPS on the internet. These weak keys were due to a widespread class of random number generator failures And they were confined almost exclusively to small network devices, things like routers and firewalls and some smart cards. Henninger et al. Then embarked on a major disclosure process to notify all the companies who were producing vulnerable devices and try and get this fixed. In this work, we ask, what happened? What happened since 2012? When you ask vendors to fix a vulnerability, do they do it? Did they respond to the notification? Did they produce patches? And can we see evidence that those patches reached the end user and were applied? So a little bit of background on the vulnerability. An RSA key contains a modulus n. The n is composed of is the product of two prime numbers, p and q. Now, the security of RSA depends on it being difficult to factor n, so being difficult to find p and q. However, if you have two moduli that share a prime factor, taking the greatest common divisor of those two is very easy, and you can then factor both of them. If you are correctly generating random numbers, there are so many primes that you will never have a collision. However, we found collisions. So random number generator failures are clearly happening here. And then I also note that we were able to detect, you can detect a vulnerable host by seeing if it has a factorable key. So in order to do this, in order to quantify this study, we needed to collect a lot of keys. The first thing we did was aggregate internet-wide TLS scans from 2010 to 2016. We computed the greatest common divisor pairwise for 81.2 million RSA moduli, both from our TLS scans and from some other SSH and mail protocol scans where we got more keys. We then identified vendors that were producing vulnerable implementations, and we looked at the results based on different vendors to see how they responded to the 2012 notification. We're going to have a lot of plots coming up, so I'll tell you how to read them. There was no individual group that was doing internet-wide scans for the entire period that we wanted to study, so we aggregated 5 different sources to get our data. The pink P and Q there is our baseline. That was the original 2012 study. On the x-axis, we have time. On the y-axis, we have the absolute counts of hosts, where a host is an IP address serving a certificate on a specific date. And I will point out that we have some scanning artifacts in here. I'll point them out as they are relevant in the data. Right now, you can see them around the Rapid7 data in the total number. So these two plots, the top is the total number of hosts on the internet. As you can expect, that has increased since 2010. On the bottom, we see the number of vulnerable hosts since 2012, or over time. Unfortunately, the number of vulnerable hosts has also increased since 2012. Modulo some artifacts in the ecosystem scans, we have a pretty steady increase in the number of vulnerable hosts. So that's upsetting, but we want to look more carefully. Maybe there are different stories within some of the vendors. So first, we needed to find out who the vendors were. In many cases, again, we're talking about small network devices. Nobody is changing the certificates, and they're being served with the default values from the shop. So we were able to directly identify vendors because their names were in the certificates. In some cases, like Juniper in the second bullet, there was a consistent certificate format, which we were then able to identify the vendor by using Nmap to identify vendor, or by just accessing a live IP and seeing what landing page we ended up on. We also used a heuristic that shared primes implies the same implementation. Now, this is based on where the vulnerability actually comes from. The vulnerability is caused when a cryptographic key is generated immediately after boot, and there's not enough entropy available against small network devices. So there is usually a little bit of entropy, but across many identical devices without any kind of interesting user input, that state might be the same. So we have random number generators that have the same state and then therefore produce the same prime number. So if we have a shared prime, we assume that's from the same implementation. A few notes about the original study. It took place from March to June of 2012, the original notification, and had remarkably low response rates from vendors. What you can take away from this slide is that out of 37 vendors that we reached out to about this particular vulnerability, more than half had no meaningful response. Only 5 released a public security advisory. So what do we want to see in the next couple, and once we start looking at the data? Prior vulnerability studies have had the model of a single broken implementation that was fixed, and then they had to push out this patch to many, many users. So this is like the Debian OpenSSL vulnerability or the Heartbleed incident in 2014. This is a plot I borrowed from Heartbleed. You can see within a couple of weeks after the notification, the number of vulnerable hosts had dramatically decreased. We see a really quick improvement in vulnerability prevalence. So we want to know, are we going to see the same things? We're going to look at different vendors to see what happened with them. And we're going to find out whether patch rates were improved if a vendor actually responded to the original notification. All right, if you're zoned out, now is a good time to come back. We're going to start looking at results. Innominate produces enterprise-grade security appliances, things like firewalls and VPNs, for applications including energy power plants, manufacturing, and transportation infrastructure. They responded quickly and substantively to our original notification in 2012 and released a public advisory in June of 2012. Now what we see here is that even though the total number of devices from Innominate has increased, the number of vulnerable devices has stayed consistent. On one hand, this is good news. It means they've removed the vulnerability from new products that are being added to this ecosystem. However, there is no evidence of patching happening on existing vulnerable devices. So devices that are vulnerable and are online are not being removed and are not getting patched. So a little bit of a mixed bag here. Juniper was responsible for the majority of factored keys in 2012. They independently released a public security bulletin in April of 2012, notifying about a weak key vulnerability, and then released another out-of-cycle security notice in July of 2012 after our notification, pointing users back to the original bulletin, which also claimed that the vulnerability was fixed as of 2011. Now we see that the number of vulnerable hosts has continued to gently increase since 2011, but then we see some really weird behavior in April of 2014. So does anyone remember what happened, what major security incident happened in April of 2014? Heartbleed. Right, so in the aftermath of the Heartbleed incident, 30,000 Juniper fingerprinted hosts, including 9,000 vulnerable hosts, came offline entirely. We looked into the IPs and we found that they didn't come back online either as Juniper or as anything else. So it's not really clear what happened here. We speculate that maybe nervous device owners disabled TLS on their devices, blocked scans from coming in, or just took their devices offline entirely. But we can only speculate here. IBM released a public security advisory in September of 2012. This is actually an unusual case. You'll see that we only have vulnerable hosts here because 100% of fingerprintable IBM moduli were vulnerable. This is because the IBM vulnerability was a little different in that they only generated 9 different primes, giving us 36 possible public keys. So you can see that luckily the number of vulnerable hosts has been decreasing. Both of them were correct. Yeah, so the number of vulnerable hosts has been decreasing here. Again, we see some weird behavior right after Heartbleed. It looks like some stuff came offline, but then eventually returned to its levels pre-Heartbleed. Cisco produces a wide variety of non-vulnerable and also vulnerable routers and security appliances. They had a substantial private response in 2012, but did not release a public advisory. And what we see is that the vulnerable population continued to rise for several years after notification, only leveling off in 2015 and starting to decrease in early 2016. When we looked more carefully at Cisco models, which we could identify based on their certificates, we found that many of the vulnerable models have reached their end of life date at this point. So this suggests that the patching, rather than having an active patching infrastructure, they sort of find vulnerable devices and then have them reach their end of life. So eventually all of these things will come offline, we expect, but this is not a very rapid method of removing a vulnerability. HP had a substantial private response to the original notification, but did not release a public advisory. Again, we see a gentle decrease in the number of vulnerable hosts, which is great. There's something weird happening at Heartbleed again. According to reports on the internet, the vulnerable integrated lights out management cards crashed when they were scanned for Heartbleed and required a full reboot to come back online. So we see that here. Linksys did not respond to the 2012 notification. And on one hand, we do see a decrease in the number of vulnerable devices. However, it seems to be directly correlated with the decrease of total Linksys devices online. This suggests that there's no active patching effort. Vulnerable devices are just coming offline as all Linksys devices come offline. Finally, we have Huawei. They introduced the vulnerability in 2014, and we see a rapid increase that continues to go up. We notified them as part of this study, and they responded quickly and released a public advisory in August of 2016. They claimed that the vulnerability was not in new Huawei products after 2013. Now, there are a few things that we can learn from this. First of all, we wanted to look into end user patching behavior. Unfortunately, we only had limited visibility into this because very few vendors released a patch. However, what we do see is that patching rates are low. In most cases, it looks like the decrease in vulnerability is due to general device churn rather than any intentional and active patching effort by users. And in particular, this low patch rate is sort of distressing when we start to think about the Internet of Things space. Internet of Things devices have a similar profile to the devices affected by this vulnerability. In many cases, people turn them on once and ignore them. So you et al. Have talked about some alternative frameworks for improving the patching infrastructure for Internet of Things devices, but this remains an important open problem. Finally, we note that vulnerability publicity campaigns like the one surrounding Heartbleed, while certainly effective, can also have unintended consequences that you can see in other places. However, these dismal patching rates underscore a more important fundamental failure in the vendor notification process. Out of 42 vendors that we notified in 2012 and in 2016, only 16 of them had a discoverable security contact. This means that we were reaching out to vendors who didn't even have a method of learning about vulnerabilities. Out of the ones we did manage to contact, few of them released a public security advisory to notify their users that there was a problem. And there's work that demonstrates that regulatory organizations like CertCC might increase vendor responses, but don't result in a significant increase in end user patch rates. So what we have here is sort of a situation where device vendors are unable to learn about vulnerabilities that they have and don't seem to have any kind of infrastructure for creating patches and pushing them out to their users. So this is upsetting. Finally, I'll end with a few comments about the role of standardization in all this. RFC 4086 is called Randomness Recommendations for Security. It says two relevant things that I want to point out here. First of all, care must be taken that enough entropy has been added to the pool to support the output use you want. So basically be sure that you seed your random number generators with enough entropy for your uses. This is good. We can all agree with this. However, in practice, what we find is that developers use dev-urandom because nobody wants to wait for their cryptography. So we already sort of have a disconnect here. Second, the standard suggests that one has to gather a sufficient amount of entropy before it can be used as a seed, mixed and used as a seed in a pseudorandom generator. This stems from a paper by Schneier et al., which has a recommendation, which recommends essentially this. You have to have a threshold of entropy before using it in order to prevent an iterative guessing attack, where an attacker can sort of cleverly guess what your entropy is going to be and therefore predict the state of your random number generator. If you set a conservative threshold, what we found in practice is that these small devices at boot time do not reach that threshold. And we end up with a vulnerability where they're all generating the same prime numbers. So while this is a valid vulnerability to worry about, we found that this recommendation directly led to our vulnerability. So what I will end on is that I think that this underscores the need to have a continued dialogue between standards writers and developers and also security researchers to make sure that we're writing standards and creating an ecosystem that is effective and feasible and also secure. Thank you for your time, and I will take any questions now.
Thanks, Marcella. Questions, comments? I have one. I said before I asked Marcella to bring this work here because I'm really fascinated with studying the lifetimes of devices that we don't think we can change easily, both in the IoT, the consequences for V6, hefty eyeball stuff. I'd like to do more in Maprg about tracking vulnerability lifetimes of devices, and this is just one of them. And the other comment is the IETF guest day thing that allows academics to come here without paying for a day is one of the reasons why we were able to bring CVs here. So I don't know if Marcella used that program, but I don't know if Marcella used that program of guest day, but I think Will did. He's coming up next. Stuart, did you have a comment?
Just a quick comment, Stuart Chash from Apple. Thank you for a very interesting presentation on an important subject.
Thank you.
All right, we have Will up next.
Cool. So I'm Will. I'm going to talk about some of the work that's been going on looking at open data sets around internet censorship. And so I'm going to sort of do this in 3 parts. I'm going to start by looking at 3 of the major projects that are going on that are collecting data and the data sets around it. And then I'll go on to what sort of the sense around censorship online looks like. And then I'll finish off with a couple ways that I think there are opportunities for interaction between the standards and governance communities and these groups of researchers. So the first thing I want to talk about is a project called UNI. The Open Observatory of Network Interference is a project that's come out of the Tor project. And so this started so it's been going since 2012. It's basically been a mechanism for individuals to debug their network connections and understand what is happening between them and the broader internet. So it started as sort of a bunch of Python scripts to detect middle boxes, detect domains that weren't loading, and specific signatures of what might be happening there. And that's sort of been an evolution where it's now moved much more towards the broader sense that it's not an individual measurement that's maybe interesting, but trying to say, can we extrapolate from this to broader country level things? What's happened there in the last year and recently is there's now a mobile app that came out for both iOS and Android, and the code base got rewritten into C to support sort of having a same set of measurements happening both on mobile and on desktop things. As part of that, there's 3 sort of standard tests that are happening everywhere now. Checking HTTP connectivity to a specific list of domains that are deemed interesting, a specific set of sort of slightly malformed HTTP requests that end up revealing a bunch of interesting middle box behavior, and then standard network diagnostic speed tests to MLab locations to look at your network speed. Also, as part of sort of taking this to be a broader thing, it's now a web-controlled thing. You can look at the current user interface that you might have if you want a deployment of this code running on desktops at demo.probe.uni.io. But it sort of looks like this. You can have a bunch of these and run tests on it. And they correlate this on their website. And so they've got 37 million total measurements. A lot of these end up being older versions of the measurements. So you're not going to be able to run the same analysis on all of them. But as part of this most recent code rewrite, it ends up being, I think, a lot more regular. So there's starting to be this longitudinal set of measurements that are coming out. There's roughly 1,000 distinct sort of end user measurement points per day happening right now, and maybe 2,000 or 3,000 total measurements from those points. Here's a couple sort of additional things. The list of URLs that are deemed interesting is one of the things that the community has come together on. It's maintained by a group called Citizen Lab in Toronto. And that is on GitHub. They take pull requests to add new domains that are deemed interesting. And the base C code that this stuff is running off of is called Measurement Kit. Cool. The second one I want to talk about is a project that I was working on as a grad student at University of Washington called Satellite. This is looking specifically at DNS consistency issues. This graph is looking specifically at how many domains in the Alexa top 10,000 were resolving incorrectly in Iran over the last few years. And we were able to generate this for a bunch of different countries. The basic thing we were looking at was using open resolvers. We found 7 million active open resolvers, and we're querying them each week against the Alexa top 10,000 and continue to do that. Their response, since those resolvers are within these different administrative domains, is similar to what someone within those countries would see, because they have to recursively do the resolution and will have the same resolvers. And so you're looking at, again, this sort of broader thing of not individual points, but what do you get in aggregate? If everything within a single AS or within a country location is returning a different thing than everywhere else, you can start to make inferences.
Did you do anything to mask the port?
Of the DNS requests?
Yes.
We were just looking on 53. And no DNS sec or any of these newer things. It was just a record lookups. This is a thing that a bunch of the academic, or this sort of technique is something that has been starting to get explored by academics, in that it is interesting to be able to release all of this data. Since I don't have anyone in the country that's actively cooperating with me, I can feel a little bit more ethically safe about then publishing the whole data set. There's a group at Princeton that's doing the same thing at a TCP level using fragmentation buffers, leaks, to understand if two remote machines can connect and establish a TCP connection, or if that fails. So this is happening at a few different layers. Finally, and we're storing our stuff on scans.io, I guess is the final thing to mention. And that Census and scans.io have become sort of these data repositories for a bunch of these full IPv4, at least, wide scans of HTTP and DNS probing. And those have now become very large repositories for that sort of stuff. Cool. So the second thing is sort of what do we see with censorship at this point? There's 4 countries that the DNS stuff is sort of showing are doing large-scale, countrywide manipulation of DNS responses. Iran, Turkey, China, and Indonesia seem to be the ones that are affecting a significant number of Alexa top 10,000 domains will resolve to weird IP addresses. There's 12 countries that UNI continues to show have explicit block pages for some domains. So you'll see a government issued block page at some point where it's not necessarily an ISP. And then there's many more where UNI has come up with specific reports of connectivity failures, but there's no specific attribution that you can do. Or it's harder to understand if this is an ISP or some ISPs versus where that directive came from. I guess the takeaways beyond that at a slightly higher level, a lot of interruptions tend to happen around elections or politically sensitive times. A lot of times the censorship is at an ISP level. You'll see divergence in how different ISPs implement something. So you'll see DNS getting blocked by some ISPs, whereas an IP block will be put in by others, because there's a lot of leeway there where there's not necessarily a technical way that ISPs get told they have to enforce something, just that they have to enforce it and they get to choose how to do it. And then I guess the final thing that I'll say is that I think some of these open measurement things are starting to show their age, that we're seeing a lot more censorship happening at an application layer within social media platforms, within mobile apps, when stuff isn't fully public It's much harder to discover. And it's much harder to say what that means in a broad sense or track it. So I guess that then moves into sort of the opportunities for standards and governance. A bunch of these scans are now all happening in sort of a common data format, which is sort of converging to this new line separated JSON representation of what a specific measurement looks at, and is working towards having these different efforts be able to do their analysis with similar tools. I think we're getting to a point where there is room to have standards for what that actually looks like and what you would expect a network measurement of this sort of type of, I attempted to find connectivity at this layer between these hosts, did it work or not, and what was the failure mode. That's getting tracked longitudinally at this point, and figuring out how we represent that and all agree on what that should look like is a potentially interesting thing to go down. Figuring out ground truth of whether a measurement failed is something that we could use help with. So for instance, on DNS, if I get a specific IP address, how do I know if that actually is some CDN edge node or not? There's a lot of heuristics we can use, but it's also nice to be able to somehow ask Akamai, is this one of your IPs? Or ask one of these various cloud hosts, right, where it's distributed. Sometimes you can't necessarily know just because it doesn't have the reverse pointer you're expecting or something. Maybe it is just because it's in some other ISP's data center or whatever. So figuring out ways to expose ground truth to researchers is a fun opportunity to think about. And of course, there's lots of conflicts and trade-offs in doing so. And then the final thing is that these measurements that we're doing from end users and from edge positions are sort of half of the story. And the other half of the story is the traffic that services see. So if you are a large service, think about ways that you can talk about aggregate users that you see from different places, and your ability to, if you can have that in near real time so that you can see when there's a drop off or where there's changes, that's equally interesting. And starting to think about whether that's something where we can get those service side user counts, even if it's a normalized count. So it's just a fraction of users that dropped off from a specific network. That's really interesting to get this picture of when there are policy changes. Cool.
Janlenkova, a Russian citizen. I actually do not think that, for example, Alexa list will be representative, because I would expect that some country will be mostly blocking their local resources, which probably would not even get on that list. And I don't know if it makes your life easier or not, but Russian government officially publishing the list of sites ISP is supposed to block. So you can basically look at that list and see what should be blocked.
Yeah. So there's a bunch of countries that have these lists in various forms. For a while, I think Thailand was publishing it in the newspaper once a week, their list of new domains as part of their notification. The approach that UNI has taken and that is in this Citizen Lab GitHub repository that I had the link to in the slides has country-specific lists that they'll test. So based on the country that a client comes from, it will attempt to get the list of domains that are interesting to that country, and generally is selected to have a list of blocked and unblocked, or expected to be either blocked or sensitive domains. The downside there is that that's an hand-curated list, so it's again not representative of necessarily sort of what ground truth experience is. Figuring out what ground truth experience is in that sense is pretty hard.
Just to share an anecdotal story, I know that at some point the site which has this list itself and the top of that list.
Thanks, Jen. So we'll do Tobias next, and then we'll go over here.
Tobias Berlin. I'm wondering if you're accounting for geographical load balancing. So if you are you're using a ground truth DNS query, I guess, from wherever you're measuring, comparing that to the DNS requests you make via the open resolver, are you accounting for example, load balancing if there's a CDN used?
Yeah, so we tried to be pretty conservative. We have a sort of a decision tree that we walk down, where basically at the top level, it's saying, is this a single homed versus a multi-homed domain? If over 75% of the global total of responses are all to one IP address, then if some specific location diverges from that, you can start to say, well, we think this site always should have this IP address, but here it doesn't, so that's a problem. And then if that isn't true, maybe almost all of the IPs that are returned have the same reverse pointer tree, and some don't. Maybe almost all of them are within a single ASN, but some aren't. So you start to try and figure out what is a characteristic of correct responses and then find divergences from that.
Quickly follow up. Do you have a notion of how many Alexa top 1 million do actually not use like the CDN or are not shadowed by something like that?
We found, so the last time I looked at this, it was roughly, so in the top 10,000, so that smaller thing, about 60% would respond the same way across all things, and about 40% had geographic differences.
Hi, Dave Dolson. A question about the social media point you made. Does that mean social media sites like scrubbing URLs from forums and preventing people from sharing URLs that they censor? Is that what you mean by that?
Yeah, I mean, anything, so either the network blocking specific stuff within Facebook or whatever. So even if that's URLs on HTTP sites, if those aren't public links, it's very hard for anyone externally to objectively measure how frequently that's happening. But then also stuff that's happening at the self-policing level or directives to these social media things where it's only observable within the application protocol are difficult to get external measurements on.
So the social media sites are preventing people from sharing these links. Is that what you meant?
I think that's one form of it.
Okay. And do you have any idea what they base that on, those lists?
It's a mix of internal policy of their community standards or directives that they get from the countries they're operating in.
All right. Thank you so much, Will, in bringing this project and work to us. That's it. We finished in slightly under time. I guess we can like last call for questions or comments, especially anything that would lead to the measurements that you want us to solicit for the next meeting. I think we're tentatively intending to meet in Prague, but obviously it has to be arranged.
If you have any announcements to make, you have a chance now.
Going once, going twice.
The IETF chair.
Allison. So yeah, so our new IETF chair, Allison Nathan. Yeah.
I feel it's okay for us to mention that the deadline for the I don't know if you did already, the Applied Networking Research Workshop is April 3rd. So there's a lot of great work here. I would hope that a bunch of people would submit to that.
Yeah, so that means in Prague, we're going to have two, I mean, a lot of the kinds of work that's presented there, at least the measurement work is similar to what we'd have in Maprg. So you kind of at least double the time in Prague, right? You're going to have a weekend, a half day session.
Right. I should have said I'm Allison Make It, and I'm the IETF chair.
And for the workshop, there are also two formats, like a long paper and a two-page short paper. So if you not have like everything sorted out yet, but you have some ideas you want to discuss, it's also a good place to go to.
Right. So from this group alone, we should be overwhelmed with submissions based on the track record. So
hopefully, yeah. Thank you, everybody. See you in Prague. How was the talk yesterday? Yeah, I had to share. But you have another talk in might get more.
Sometimes I
I thought
And